and then we'll do our break. In the next section, I want to briefly discuss the Rabin-Karp algorithm as the last example of string matching. And it's a slightly different type of algorithm. I think it's interesting from many respects, but again, like the Boyer-Moore, it's not part of the exam for us. But it has a few other interesting characteristics it's worth knowing about. Okay, where are we? Knuth-Moyse-Brand has the best worst case that we've seen. Boyer-Moore seems to be better on average, at least for non-pathological text. So what else really is there to hope for? Well, both need extra space. Now, I mean, to be completely honest with you, I don't think that's such a big deal because the extra space is as big as the pattern, and we have to store the pattern while we're searching. So it's if you ignore constant factors, it's not such a big deal. But as a theoretical, like I wish I had the little theoretician professor on the slide here. At least theoretically speaking, it would be nice if we can avoid that. Can we do efficient pattern matching, more efficient than brute force, without having this extra space? And it turns out the answer is yes. And the answer is interesting for other reasons. It's the only point in the module where we'll talk about hashing. Hashing in principle is the idea that you take a complicated object and you reduce it to a single number, an integer. That's something used in computer science for various things. It's usually introduced in the context of hash tables as a data structure, an alternative to binary search trees. And they have very interesting stories behind them that we won't get into. But you can also use hashing more loosely to compute a kind of fingerprint. And that's the sense that the Rabin-Karp algorithm uses hashing for. So roughly speaking, the idea is we compute a fingerprint of our pattern, and we compute fingerprints of parts of the text, and only compare the fingerprints first, which supposedly is very cheap because they're all just short numbers. If the hashes agree, if the fingerprints are the same, then we check the actual pattern. Now, I should comment on the term fingerprint in this case. If you think about human fingerprints, then we think of them as unique. And as far as I know, they are. Question? Yeah, so fingerprints, human fingerprints are used as ID and for authentication and all that. I mean, it's not so sci-fi anymore. Most phones have that. So fingerprints for humans tend to be quite unique, right? If you take two humans, their fingerprints are usually different. Unfortunately, in computer science, a fingerprint is not unique. So our fingerprints, it's a very standard term. Where it comes from is, instead of the entire human with all the complexities of your personality and whatnot, I'll just take your fingerprint. It's a short summary of what you are. That's the way in which fingerprint is understood here. So don't think of authentication as in this section. Think of it as a short summary. And now, if you think of this from the perspective of compression and retaining information, if you have a really, really long text and you condense that to a small number from a certain range, there's just too many texts for that number to be unique. So you will have different texts, maybe even of different length, that both get assigned the same number. So our hashes will necessarily have collisions, which means there's different objects that get the same fingerprint. And the whole story about hash tables is how to deal with those and so on. But again, something we haven't got the time to cover. In this section, it's convenient to assume that the alphabet are just our standard digits. Then we can use as the fingerprint just numbers. And they have the natural meaning of numbers as writing digits one after the other. So here's an example of a text and a pattern. And here's an example of a hash function. That's what is a hash function is what computes the fingerprint, what computes the summary. Again, in biological terms, it doesn't make sense. There's no function that takes U as an input and spits out a, oh, that sounds gross, like chopping off fingers or so on. Let's delete that. In the computer science terminology, you have a way to input a complicated object and it computes a number for you. And here we just take the number modulo a prime number like a 97. It's not necessarily prime. But no, it is. Yeah. Okay. So we take our pattern. Now you have to take my word for it that 59,265 modulo 97 is indeed 95. I'm not gonna double check now, but you're welcome to do it. And what we do is we take portions of our text and also compute the hash. So if you do this for 31,415, modulo 97 gives 84, I hope. And if you take the next digits, 14,159, you get 94, and so on and so forth. Until at this point, you indeed find the same, that's an occurrence of the pattern, so it has to have the same hash. And once you find that the hashes of the pattern and this portion of the text agree, then you have to do your character comparisons. At that level of abstraction, the code for doing that is not very complicated. We'll always restrict ourselves here to hash functions that take a number and to compute the remainder of division by a prime. So I'll just leave it with find a suitable prime number. And the choice has something to do with the performance guarantees at the end. Then we compute the hash of the pattern. We take the entire pattern, compute a number from it using essentially that scheme. So you interpret the digits, the letters as digits in a number of base sigma, and compute the modulus of that number with respect to m. And then you iterate through all positions in the text. You compute the hash of the appropriate portion of the text. If the hashes agree, then you still do the check of the pattern against the text. And if it matches, you return that position. Otherwise, you continue. So I should point out that this is not a constant time operation. I'm just writing equality on an entire string, assuming that this is actually a loop over the characters. That's just to keep the code a bit shorter. We never miss a match if we do that, because if there is an occurrence in the text, then the hashes at that position of the pattern must be the same. And then we do the explicit check. And if the hashes don't match, then certainly also that position of the text and the pattern are different. The problem with this code, or why this code is not exactly useful, is that computing this hash value of a part of the text also takes time proportional to the length of the portion of the text. So it takes m time, roughly, because you have to at least read that part of the text and deal with the numbers. So it would give us an overall running time of just the standard brute force algorithm. So why bother? The reason is that we can modify how we do this part, how we compute the hash of each of the portions of the text to be much, much faster. And then it becomes interesting again. The way to do this is to update the hashes instead of recomputing it from scratch. And I'll just show you in an example why this is possible. We do some pre-computation, then we have one hash of a portion of the text. So you should imagine the text has these 9 digits, and then it continues with 6. We currently have the hash of that part. Once we're done with that, we want to shift one character over to that portion. Now these two numbers, if you just look at the numbers, they're very different, but they have a long part in common, namely all the middle digits. So how do I get from 41,592 to 15,926? Well, I subtract 4 times 10,000, multiply the number by 10 to shift everything one position over, and add the 6. And the magic of modular arithmetic allows you to do all of those operations on the remainders with 97. So here's that spelled out. That's the new hash we like to compute with the one position shifted over. What we have is the old hash. So this number modulo 97 is what we know. We can get from that number to that number if we subtract 4 times 10,000, shift by 10, multiply by 10 to shift all the digits, and add 6. Okay. And we do then compute modulo at the end, but modular arithmetic allows you to shift the mod inside. So we compute the mod here first and take our known hash from the previous position. Then we take 4 times the hash of 10,000, which we pre-computed. And the rest of the operations are all involving short numbers. So the important bit, imagine these 5 digits are 1,000 digits, the length of your pattern. Then these two numbers are really big, but all numbers in the second line are very small. They're at most m. And so if you compute the result from that, you get the next hash. And at least on the word RAM, all of that can be done in constant time. So more specifically, here's the full code. We use a radix for our numbers, and by and large, you can use the size of the alphabet. A power of 2 is convenient to do the shifts with just shifting digits instead of a multiplication, but that's it's a minor difference. Then you have to choose your prime to be a large enough prime. So something bigger than sigma for sure. Maybe not much bigger. If you do that, all the numbers are bounded by this value. So you can do it on a word RAM in constant time to update the hash. And the update of the hash is spelled out in this line. And the rest has remained the same. We find the hash of the pattern up front. We compute the first hash from scratch of the first portion of the text. But from then on, that's the same code as before. Whenever we have to shift, we compute the next hash of the portion of the text using this update formula. Now, the analysis is a little tricky because we have this part where we sometimes have to do the m comparisons. That should be double equals. So this is the expensive part that takes m comparisons. And it's not so obvious how often we have that case. If somehow the universe conspires against us, there could be many parts in the text that hash to the same hash value as the pattern, even though they're not equal. And so we might have to do many comparisons, even though there are few occurrences to report. Or we report the first one anyways. If you randomize the choice of your prime or randomize the text, the expected running time of this algorithm is best possible, linear in both, order m plus n, like k and p. But the worst case still is this n times m, if, as I said, the universe conspires against you and you always have portions of the text that hash to the same value as the pattern without being an actual match. But if you put your prime large enough and add a bit of randomization, this is very unlikely. And so it's one of those cases, as for random binary search trees and quicksort, where we chose a random pivot. By and large, it's fine to use it, even though the worst case is not as good. You can prove strong guarantees on the expected running time and high probability bounds. What's also useful, this algorithm can be extended to other situations where you don't have just strings, but 2D pictures, for example. The kind of fingerprint can be extended to that, whereas many of the other methods like KMP don't easily generalize to that. And coming back to this initial motivation, it only uses constant space, because all we need to store are these extra hashes. So we pre-compute the hash of the pattern, and we maintain this hash of the text. That's all it needs, plus a few extra index variables. So among all the string matching methods we've seen, that's the most space efficient one. Well, apart from brute force. I again have a clicker question like the same type, but I'll skip this one, and you can do it at home. Ask if you have questions. And I'll close with a little bit of an overview of all the methods we've seen in this unit, and another one that we will see later. Just comparing their different performance characteristics. It probably would have been better to ask you to do it and read through the chapters, but there you go, for convenience.